In our last lecture, we were discussing on external direct product of two or more subgroups or groups. Today, we will discuss on internal direct product of two subgroups. Let us recall both the definitions. Let us suppose we have a subgroup H1 having elements A and B, and we have one more subgroup having element which is H2, and there are elements of this H2 are let us suppose 1 comma 2. Then the external direct product of H1 and H2 will be written as H1 cross H2. Here you will use the cross product, cross symbol, and the elements of this H1 cross H2, the element of this set will be ordered pair of the elements A with 1, A with 2, again B with 1, and B with 2. We will write such type of ordered pairs, and these ordered pair will be considered as an element of this set H1 cross H2. This is the definition or way to find the external direct product of two or more subgroups. Today we are going to discuss as internal direct product. Let us suppose we have the same elements H1 and H2, and we want to write their internal direct product. So their internal direct product will be written as directly H1 H2 without using any symbol between H1 and H2, and the direct product will be written as the product of A with 1, that is A, the product of A with 2, that is 2A or A2, the product of B with 1, this will be B, and the product of with 2, it means 2B. Here we will use the direct multiplication, not the ordered pair. So this is the definition to write the internal direct product of two or more subgroups. So as per the definition, let us a group G having some normal subgroups. Please note it carefully. That is, it means the internal direct product can be written as the product of two or more normal subgroups. H1, H2, Hn, these are n normal subgroups of this group G. Then this group G can be defined as the product of these n normal subgroups. So this product will be equivalent to G, and this is the definition of internal direct product. Let us take a theorem based on internal direct product. In this theorem, it is stated that if H1 and H2, these are two normal subgroups of a group G, then this G can be written as can be written as the internal direct product of H1 H2, which is mentioned in our definition. And on another hand, there will be only one common element between H1 and H2, this which will be identity. So their intersection cannot be empty, and in the intersection of H1 and H2 we will find the identity element. And this is the necessary and sufficient condition. It means if these two conditions are fulfilled here, then H1 and H2 can be written as the normal subgroups of this group G. And if G has two normal subgroups H1 and H2, then these two properties will be satisfied. So here we will prove this theorem in both way, necessary condition and in sufficient form. Initially we are assuming that G is the internal direct product of their normal subgroups H1 and H2, and we will prove the given two conditions. If G is a group, it means it will contain at least one element. Let us suppose this is G. Because this G is generating by the internal direct product of these two elements H1 and H2, let us suppose this H1 has the element H1 and H2 has the element H2. In this way, H1 has the element H1 and H2 has the element H2, then their internal direct product will contain the element of this type H1, H2. So this G, because G is the internal direct product of H1 and H2, so this G will be formed by the product of these elements H1 and H2. Let us suppose G is the equal to H1 and H2, where H1 is the element of first subnormal groups, and H2 is the element of second normal subgroup H2. So as per the definition, H1 and H2 will belongs to H1, H2. Here we can see that this is equivalent to G, and we are assuming any element in capital G and we are solving that element in H1, H2. It means every element of this group G is available in H1 and H2. So G will be the subset of H1, H2. On other hand, we are saying that this G is the internal direct product of H1, H2. It means the product of H1 and H2 is trying to generate G. So H1, H2 may be proper or improper subset of G. So H1 and H2 can be treated as the subset of G. By using these conditions, we can say that G is equivalent to H1 into H2. Again, we are assuming that let us suppose any element G which is available in the intersection of H1 and H2. Because G can be written as the product of, with identity, it means this G as well as this E both will be available in the intersection of H1 and H2. So we can say that identity will also belongs to the intersection of H1 and H2. Conversely, we will assume these two conditions, we will use these two conditions, and we wish to show that G can be written as the internal direct product of H1 and H2. Let us suppose, because G is equivalent to H1 and H2 and we are assuming any element small g in G, so this G will be also belongs to H1 and H2. Because the nature of G, because the G is belonging to H1 and H2, the product of H1 and H2, so the nature of this G will be, it means it will be generated by the product of two elements. The first element will come from H1 and the second element will come from H2. So this G can be obtained by the product of two elements H1 and H2. The first will belongs to capital H1 and the second element will belong to capital H2, which is mentioned here. If it is possible that G is the product of another two elements H1 dash and H2 dash, we are assuming that G is the product of two different combinations. This is our initial assumption and it is another assumption. As per this equivalency, the first element will belongs to H1 from both relations, so H1 dash will also belongs to H1, and the second element H2 and H2 dash will belongs to from the second subgroup H2. Because H1 is also a subgroup, so the inverse of each element will also belongs to here. So we can write here the inverse of H1 will belongs to here and the inverse of H2 will also belongs to here. Therefore, on using closure property, because H1 inverse is also belongs to H1 and H1 dash is also belongs to H1, and similarly in right hand side, and this is belongs to intersection of H1 and H2, and here we have shown that the identity element, only identity element is belonging to intersection of H1 and H2. So it is only possible when the inverse of this H1 is H1 dash, or either the inverse of H1 dash is equal to H1 inverse. So this H1 will be equivalent to the H1 dash. This is only possibility, this is only a single possibility to write this relation equal to identity. So here no another combination is generating G. These elements are similar. The H1 dash is not different than H1. H1 dash is also equivalent to H1. Similarly here H2 dash, this is again equivalent to H2. So the G can be written as the internal direct product of elements, because the every element G of G can be expressed as a unique combination of two elements H1 and H2, first from site H1 and second from H2. No different combination can be equivalent to G. So this is the internal direct product. Let us discuss one more question based on this theorem. In this theorem, it is stated that G is a cyclic group of order 6 with generator A, and there are two normal subgroups of this group G. Then we wish to show that H and K are normal subgroups. Sorry, these are the sets, and we wish to show that these are the normal subgroups. So we will use above mentioned theorem. This is the definition of K, this is definition of K, and this is definition of H, and this is their intersection. Here we are seeing that the intersection of H and K having only elements identity. On another hand, we see that the product of HK is generating the complete group G. So here HK is equivalent to G and their intersection is empty. So on basis of previous theorem, we can say that H and K, these are two normal subgroups of G. In case of any difficulty, please contact me. Thank you so much.